the rate I'm trying to get through. Okay? Now at this point you would say, well, but I already knew this for point-to-point. I don't need to code for point-to-point, as a matter of fact. Do I? Do I need coding for point-to-point? No. Right? So obviously this is going to help me some way down the road. But right now all we've done is brought a known beloved theorem from networking that never looked at an algebraic beast in its life and have an algebraic mapping of it. Okay? But we'll see why this is useful. Okay? So by the way, how are we going to find these solutions? Okay? So remember that what I need to find is the xi's. All right. So one of two things. So what I'm looking at now is this. If I'm looking at whether M is invertible or not, I'm looking at the determinant of M. All the elements in the determinant of M are polynomials in the x's, right? Some of them are 0. So the determinant of M in the end is just a polynomial, a multinomial in x's, right? So, and this is going to be very important when we do random network coding later. If there is a non-zero, so if that multinomial is a 0 multinomial, okay? Examples of 0 polynomials are, of course, you know, x minus x, bummer 0 polynomial, okay? But sometimes it's less obvious, right? So if it always evaluates to x, to 0, then, you know, I'm cooked, right? What am I going to do? There's nothing I can do. I can't choose the epsilons, the x's anyway to make me happy, right? If I can choose them to be non-zero, it means that as I go to a large enough field, there's going to be more and more solutions. Okay? So let me look at this polynomial here. Okay? First of all, is it a 0 polynomial? No, right? I mean, the ways I can choose it to be not, right? It's not x, okay? So it does not have a non-solution. It doesn't have a non-zero solution in F2. Right? You can see that right away, right? Because it'd be either 1s or 0s. It actually doesn't have one in F3. It doesn't have one in F4. Obviously, it was carefully chosen to to have these, you know, unfortunate properties, F2, F3, F4. But it does have one. So eventually I hit it. In F5, bam, I hit it. If I keep upping the ante, going up in the field size, what's happening? Well, this has a finite number of roots. Right? It has a finite number of roots. Now, you know, it may not always be easy to find the roots, but it has a finite number of roots. And the number of roots doesn't get to grow with the field size I'm considering. So as I'm going up in field size, my number of roots stays the same, but my number of possibilities goes up. So since my number of roots stays the same, but my number of possibilities goes up, it means that more and more of my possibilities are going to, proportionally, are going to map to non-zero solutions. Right? If I have n roots, but I have a lot of possibilities, then out of all my possibilities, only n out of all my possibilities is going to be giving to 0. Okay, and this is going to be very important for the random coding. There was a question back there.
So if the rates were not normalized to be 1, then is it still an only if n is invertible?
So if the rates are not normalized to be 1, you know what? We'll look later at rates that are not normalized to be 1. So the one normalization is just to make my life easier. It would, I can parallelize. Basically, what you have to do is decrease the granularity, right? I mean, that you can ask, well, what if my rates, what if my rates are pi? Okay, run into these issues, but but that's, you see that's just a technical issue that doesn't really matter, right? It's a granularity issue.
If the rates in that case were half and half, maybe you can.
I would just double it. I would just use it twice. Right, I mean, who decides what half is? I get to decide what 1 is, and I get to decide how many parallel links I have. Okay? All right? Yes. Yes, Lalita, yeah.
So I understand F2. So when you're looking at 3, 4, I mean, these are strings, right? So how are you mapping a string back to a scalar? I must be missing something.
Okay, I have a ring of polynomials over an infinite field in certain variables, right? So map it to this. It's not a string. It's exis that I care about. Okay, so let me look now at another example. Okay, and this is an example which is not upper triangular, because the way I had set it up right before it looked upper triangular, but I told you it would see non-upper triangular. Okay, so here's my first non-upper triangular. Okay, and I'm sorry I put an upper triangular first time, because obviously this got people very excited about upper triangulars. Anyway, so here we go, and I have an example with two parallel links here. Okay, E1, E2 here are parallel. And this goes back to your question about 1/2, right? If this was 1/2, I would renormalize 1/2 to be 1, and the one that was 1 would become 2. Okay? All right. And okay, so here we go. This is my network. So I have obviously the pre-processing, the post-processing. I have this, trust me that this does it, but you can kind of go through it. You can go E1 through E4 to E6, right? Or I could go E1 through E4 to E7, or I could go E1 through E5. Okay, and just at okay, all right. But it would I guess here would if so. Okay, let me put it this way. This matrix is not upper triangular. If I had done the whole thing with the F, it would look upper triangular. Okay, but I don't want you to think that in the end the G is upper triangular. Okay, it's just because I had no cycles, the F would look upper triangular. But it's not the G that needs to be. Okay, so but the F would, of course, as before, because of the lack of cyclicality, be upper triangular. Okay, all I care now is I don't care about anything except the determinant of M. If I can pick the determinant of M to be non-zero, I can invert this puppy. If I cannot pick it to be non-zero, I cannot invert it. End of story. Okay? So now I have this multinomial and these betas, and I can pick betas to give me non-zero, or I cannot. Let's go to the multicast. And let's see why it was important to have. So remember, the first thing that we did in terms of theorem was take a theorem, which was a theorem from networking, which never required coding, and turn it into a theorem with some algebra in it. Right? The min-cut max flow, point to point. Now let's see what happens in a multicast network. Well, I have here X's, and multicast means that I have several receivers, and all of those receivers want everything. So my connection looks from V being my input to U1, cal X of V is a set of connections. So everything that's going into V, I want at U1. Everything that's going into V, I want at U2. Everything that's going into V, I want at UK. Okay? So that's what I mean by multicast. Everything that's going into the input, I want at every output. Right? So what does this look like? Well, who knows what the network is? Right? It's a mess. Okay? But all I care about is I have some matrix A, which is the pre-processing, right? Which I am only doing on the X's, not on the Y's or the Z's, right? So this is my vector of X's and Y's, right, of all inputs. Okay? And then I have a post-processing. What is my post-processing doing? Well, my post-processing is at the output only dealing with those things which showed up at this output. Right? So see, I have 3 output edges to go onto here. And those 3 output edges are only going to deal with the edges that are coming in. And over here I have 3 output edges which are only dealing with the edges that are coming in. Same thing here, right? So over here, I cannot put anything onto other output edges. Okay? Nor can I take stuff from output edges that are somewhere else. Okay? So I have this matrix with blue, red, yellow as the block corresponding to the first, the block corresponding to the second, the block corresponding to the third. All right? So what is this going to look like when I do the whole thing? I'm going to have a blue matrix, which is the matrix mapping the inputs to the outputs at the first receiver. I'm going to have a red matrix mapping from the inputs to the second receiver, and a yellow matrix mapping from the inputs to the third receiver. Each of these matrices by itself is going to look just as though I had done the point-to-point. In order for me to be able to recover the X's at each receiver, it's as though in my previous exercise, when I was just sort of rederiving the min-cut max flow theorem point-to-point in an algebraic way, it's as though I have to do it for each and every receiver individually. So each of these sub-matrices is going to be with elements that are excised, and the determinant of each of those sub-matrices is going to have to work out to be non-zero. Right? So when I choose my excis, I have to make sure that they work out to be non-zero here, they work out to be non-zero here, and they work out to be non-zero here for the determinants of these sub-matrices of M. Does that make sense? So in the multicast, I have this particular structure. Is everybody happy with this? Because it's important, particularly when we go to random. Good. All right. So now I can basically do the following. So as I said, my set of connections is defined in this way. M is a cardinality of cal V by K times cardinality of cal V, where K is the number of receivers that I have. So in this case, I have 3 receivers. K is 3. Right, but however many receivers I have K receivers. I'm just going to M1, M2, all the way through MK. Okay? So this Mi xi is the determinant corresponding to the mth matrix, which is the matrix corresponding to the algebraic impulse response viewed by the kth output. Kth receiver. Bless you. Does that make sense? So the kth receiver has an algebraic impulse response viewed through the network. This is really what the xis are. Right? This is what the M's are. So the xis are the contributions of the network towards the end-to-end impulse response, and a receiver can only receive the stuff if he by himself has an algebraic impulse response which is invertible. All right? This is it says linear time invariant system. It just happens to be over a network, and it just happens to be over a finite field. Okay? So I need to choose the coefficients so that all of these determinants of these sub-matrices are different from 0. Or the same thing to say is I need to choose the xi such that the product of these determinants is different from 0. Okay? Let's look at the time. Okay. So here's the multicast theorem. If I have a multicast network program problem, remember, what is it? It's first the graph, second the set of connections. There exists a linear network coding solution of a finite field for some large enough M. Okay? If and only if there exists a flow of sufficient capacity between the source and each sink individually. So for each sink, I'm doing the min-cut max flow theorem. And since for each sink, it's clear that it's necessary, right? I mean, the fact that min-cut from the source to every sink has to hold is necessary. But in traditional networking, is it sufficient? No. Pardon? That's right. I mean, the butterfly example that we started out with is a case in point. The min cut from the source to each receiver was, of course, 2. But it had not done network coding, it wouldn't have worked. I could not fit 2 trees onto that butterfly network. Right? Let me go back to that. I cannot fit 2 trees onto that. Right? So if I had put in 1 tree over here, going to both receivers, the other tree would have started out okay, but it would not have been able to go down here. So if I'm doing multicasting with no coding, I do a tree. I can't fit 2 trees there. But I can fit 2 bits. But I need to code. Okay? Is everybody happy with this? So you see why we started out by doing what seemed like a rather bizarre exercise in turning the min-cut max flow point to point, which is benign and known and loved, to an algebraic version of it, which seemed like something slightly perverted to do, especially on Monday morning, in a room with no coffee. But basically, this is the reason why, right? Because that point-to-point immediately gives you the multicast. Each receiver, as far as he's concerned, is a point-to-point, right? So if his matrix works out for him, he's happy. He doesn't care if it works out for the other guys or not. But of course, we care to set up the whole set of connections. It has to work out for everybody. Lalita.
Yeah, no, that's a good question. So mathematically, you can prove that there exists a large enough n to...
If it's invertible. If it's not invertible, then no. And this goes back to this theorem here. But this is not a theorem that somehow we invented. I mean, this is just a fact. Okay. Okay. Multi-source multicast. So we saw from one source to one destination. What happens if I have different sources? I have more than one source. So for instance, let me look here. I have 2 sources, and they both want to get everything to every receiver. Okay? So now what do I have? My pre-processing, some of the pre-processing is happening here on the first 3 sources, and some's happening over here on the last 2. Okay, this is my pre-processing. And then it goes to the network. Messy, 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 messy. And then it comes out. Each receiver takes what it sees, maps it to its outputs. What it sees, maps it to its outputs. Right? Looks the same. As a matter of fact, one way of thinking about it is I could just have a mega source over here if I wanted to. Right? So the number of sources, it can be multi-source, multicast, makes no difference. Right? But as many sources as you want. The main point here is that if I look at the connections, every output wants everything. Other example. Okay, so here's the theorem that goes with that. So again, all I need is that the min cut from the set of all sources to any sync node satisfies the max flow. Okay, so you can see how these things are popping out. Right? I mean, this looks trivial because I show it with a blue, but it's actually not a trivial result when you think about it. Right? So that's why we're building these eyes and slowly going through this whole thing. And here, well, I just set up the F and I just, crank it. I have no idea how deep this thing is. I don't want to know. Okay? All right? One source, disjoint multicasts. So one source disjoint multicast means that I have a source and every receiver wants something else. Maybe I shouldn't have called it disjoint multicast. Disjoint something else. But whatever. Every receiver wants something else. Okay? So I have one source, but none of the receivers want the same thing ever. Okay? So in this case, the M basically has to be able to look like this. So I have to be able to have this one invertible, this one invertible, this one invertible. Okay, I'm not showing you the theorem, but you can start seeing where this is go. One source, disjoint multicast plus multicast. So some of the things are disjoint plus some of the nodes want some stuff but nothing else. Some of the other nodes want want everything. Okay, what is it going to look like? It's going to look like this type of matrix, right? This needs to be invertible, 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 this needs to be invertible. Okay? So now everything that we're doing is just turning into, here's this matrix, I need to be able to invert this. Right? So I think 10:35, right? I have one more minute. So I'm just showing you this, not to make you, well, one, to make you look forward to the coffee break, but two, to make you see, that out of this we started out, and it was a good thing that we spent a lot of time trying to understand this matrix, and I realized there was a lot of, confusion, which I had pedagogically not foreseen because of this beta E4, E4, right? This diagonal. But now that we've got this, you can just crank these things out. They don't look pretty necessarily, but man, they just pop out. Okay. So for instance, linear cyclic delay-free network, a set of desired connections, some of which are meant for one receiver that wants that and nothing else, others that are meant for all receivers, okay? Then what's going to happen? Well, I need the min-cut Maxwell bound to be satisfied between V and the set of nodes that want everything. And for the others, I just need to be able to have the min-cut Maxwell bound with this sort of, just for that local, that local realization in this matrix here. Okay? All right? So we can see where these things are going. What do you think is going to be tricky?
Is this a typo, this UL, and then you'll continue with J indexing?
I'm sure I have more typos than I can shake a stick at, but... So I have the ones... So the one through K, they only want one set of things. And the others, union, the ones that want everything for K plus 1 through Kn. Is that a typo?
There's a needed
L.
There's an index. Oh, the U sub L should be a U sub J. Yep, thank you. And I'm sure there'll be more. Yes, I'm sure in future ones too. Thank you. Right. Here it is J instead of L? No, here I put J. No? Did I put L? Did I put I instead of J? No, this one's right. For I and J different.
But in the theorem, when you are stating the theorem for this here.
Yes. Did I put L instead of V and U, L, L? So, yeah, to be fair, these don't have to be the same. Right, the L and the J, they're just free parameters. I screwed up in the previous one because they were in the same set, but here it doesn't matter. Can everybody quiet? I need a higher SNR, so everybody quiet down or you scream. Okay.
Okay, just I want to point out to where the error is. When you are defining the set of desired connections, C, and then you have J from 1 to K, and then union again.
Ah, that's right. So this was copied from the other one. Yeah, so this should be a J or this should be an L. Thank you. But the rest is fine. Thank you. Okay, yes, more typos. No type. Oh. Okay.
From networking perspective, what does the little n in your finite field size correspond to?
The middle, okay, so we'll talk about that more later, actually. So I'm going to address that. So hold that question.
I'm just trying to interpret the statement. So cal x of v is the total amount of information that the source has to broadcast.
It's actually not the total amount of information. The cardinality of cal x of v is the total amount of information. This is the total set of processes. Okay?
I would suggest we let Muriel get coffee.
Yeah, obviously you would. Great. Okay, so we'll but there are no burning questions at this point, right? Except that one, which. Okay, good. Let's go. Thank you.
Start again shortly after 11.
Just maybe make
Yes.
a remark.
And one
Yes. Which one?
One announcement.
Just this
Professor
one.
Yenner has a.
Just a couple of remarks. So we'll start the next lecture at 11 sharp. And we're going to the coffee break, and all the food is always going to be at 101 East. And I'm going to be going around with a bell 5 minutes before, so you guys make it on time. Just one more thing. This is a very big class, okay? And this room is very unforgiving in its acoustics, in that if you ever whisper, even at the very back, the instructor here can hear you, I can hear you, so it's very disruptive.
And can see you.
I can see you, I can't, but you can. So if you must say something to your friend, wait for 90 minutes.
Okay.
Right? And we encourage questions a lot, but just to the instructor, not between yourselves during
Great.
the lectures. All right?
Good. Thank you. So I think this one. Okay, I'm fully equipped. So, all right. So let me get restarted. So when we finished, we were at this point, and obviously you guys were already starting to catch typos, so you were all on top of it. And the main output from this morning is we have an algebraic impulse response to the system, and the question is whether we can invert a matrix or not. Sometimes the matrix can be a global matrix. Sometimes it's just going to be a local matrix at a particular receiver. Okay? And from this very simple approach, we can do a variety of things. So we can also do one source, two level multicast, where one person wants everything, one set of receivers wants everything, and another person or set of receivers only wants a subset. Three-level does not work in general. Okay? It's like, so many computer sciences that say, 2 is easy and 3 is as hard as anything else. We'll go a little bit more into that this afternoon. But anyway, we can do this two-level multicast. We can have an acyclic network, which is given with a set of desired connections. And the network problem is solvable, again, if and only if the max flow bound is satisfied between V and U1. Okay? I'm not going to go much into the reason why it in general doesn't work, but you'll see later. You'll see later. Delays. You have all been longing for delays. I can tell, because I've been having a lot of questions at the break, and I think before that also have to do with delays and so on. And before we go into cycles, let's go into just delays. We can transmit random processes with a delay. What do we have to do? We have to put a delay variable, and then we're going to have to put a second, basically a second aspect here, which is the accumulation of delay as we go through the network. Okay? So now what I'm going to do is I'm going to have, instead of just having a process, I have a process which is a polynomial in D. Okay? And that polynomial in D is, in effect, the process at time L, or the process X corresponding to delay L. Okay, so this is basically giving me a sequence in time. All right? So some of you may have seen Z transforms, some of you may have seen D transforms. It really sort of depends on what your background is. Some of you may have seen with something with Z to the N, sometimes it's Z to the minus N, okay? It doesn't really matter. All you're saying is that the power that goes along with this free variable, Z or D or whatever you may have, corresponds to a time shift. All right? So whatever your background is, Z, D, or whatever it may be, or Z inverse, okay, just think of it that way. So we have a set of input processes. We now have the delay in there. So it does not any longer need to be static, which goes back to the question, oh no, now you moved my cheese. People moved. Okay, whatever the question, whatever the question was back there by Stephanie, was it? She was walking here. She got lost in the stairs. Okay. Anyway, yeah, this is not a lossless network, these stairs. So whatever the process was, now we're going to have a D in there, and then the output also is going to be in D. Okay? So we're going to not have necessarily a one-shot deal with a sort of implicit delay. We're going to have an explicit delay. But the fact that we have these polynomials in D may allow us to do more things, but from the point of view of our structure, it really does not change anything. So whereas before we were considering X as sort of a single shot or a process, it didn't matter because it was time invariant, now I'm going to consider D actually still as a single shot or process. Okay? So the same thing has happened before, right? I'm going to have the output of a node be a linear combination of the exogenous and endogenous inputs at that node, except that I'm going to pick up one delay as I step through a link. Okay, so I'm going to multiply by D the random variables. Okay, so let's go back to this one because this served us so well the first time. But again, modulo this question of, should we have a diagonal, which in the end would give us nothing because all it would do is allow us to have this beta E44, which I can leave in there, but it would just mean that I would never get to 0. I could keep, going around and around. Summing the path gains, what I'm going to have is the same thing as before, except that now I have a D squared when I go through a length 2 in terms of edges, not in terms of nodes, but in terms of edges. Okay? And, in my incidence graph, which is still over there. Okay, so every time I step through one more edge, I get a D, so the length is going to be represented in the number of betas in this element which indicates a path for going from one to the other, from one point to the other, but also with a d with some sort of power representing that length. So here I have beta times beta, I have d squared. Here I have 1 beta, I have d. Okay? And everything that we did is going to hold as before, except I have to drag these d around. But everything that I did before, for instance, the point-to-point, min-cut, max flow, this, of course, looks as before, because this is a non-algebraic animal. And here I'm going to have a determinant, except that I'm going to have these d's. But in the end, what do I need? I still need the xi's to give me something that's non-zero, but these coefficients are going to be over a field of rational functions with these d's. Right? So let's go back and look at this. What does it mean for me to be non-zero? It means that when I look at the determinant of this, I have the betas, I also have these d's, and I need to have non-zero polynomials in d. Right? So it's non-zero. The d doesn't matter. The d is not my problem. It's still the xi's. Let's put it that way. Right? So I'm looking, instead of looking at a polynomial in xi, I'm looking at a function of d. But that function of d is entirely, once I know that function of d, once I know where, what the powers of d are, is only really dependent on the xi's. So I'm back to just having to have the xi's work out. Right? So now I'm looking at having non-zero functions of d rather than just having non-zero one-shot matrix determinants, right? But it doesn't really change my life. Again, if I chose the betas to be 0 here, it's not going to be good, right? Or if I end up with a function which is d minus d, not good. Okay? D squared minus d will be okay. So now I have to study the solution sets of polynomial equations over this slightly different new animal. And now at receiver nodes, of course, I need to have to allow for memory. Okay? Okay? So again, something like d minus d would not be a good function. D squared minus d would be okay, even though without the d, 1 minus 1 would not be good. Okay? Yes?
The coefficients in these polynomials that we choose in designing the code, are they also rational functions in D, or they're just
no, we're looking. The xi's are going to give me functions in D.
Functions of. So the xi's themselves are.
When I pick the xi's,
yeah.
They give me a function of D as my impulse response. So now what do I have? I still have a linear time invariant impulse response. Now it's a linear, but I have delays in it with memory. It's not a one-shot.
And I guess the 2 is binary?
Pardon?
It's over the binary?
Yes, I can do it over the binary. Yeah. Was that the question?
My question was that the size themselves, or size themselves, they're elements in the small field, like in this case F2. They're not. Size are not rational functions.
The xi's are not rational functions. I'm sorry. No.
The computation being performed at the vertices is still.
The computation being performed at the vertices is still this one. It's a one. At the vertex, when I'm doing, I'm doing this. Okay? But before, all I said is I need my determinant to be non-zero. Now, there's no such thing. The determinant, what does it mean? The determinant is itself a function of d's, right? Yep. Which allows me a delay. So I need to make sure that the function of d doesn't turn out to not be 0. Okay? So basically, was this? Okay, so just to give you some idea, one of the things that this does is you can prove certain things, which I'm not going to write here, but in the original paper by Alsved et al., there was a question actually, if you had delays, as to whether you could have a time invariant solution. Right, there was a question that was posed there, and they had suggested a setup which was a layered setup in which one network layer basically fed into the next network layer time after time after time, and it had sort of the spiraling effect. Okay? And that was an open question. Can you find a time invariant solution? And the answer using this is that you can. Okay? You can find a time invariant solution to the whole system, but you have to look at it with this delay. Okay? But you don't need to change things with D. Right? You still choose exis once and for all. So if you can do it in the multicast, you can choose exis once and for all, and using those xis, blithely go through. Okay? Yes, Paul?
So we want the determinant to be non-zero, and
No, I don't know. It's not that we don't want the determinant to be non-zero. The determinant is no longer a determinant in the usual sense as before. It has D's in it. Okay?
My question, I guess, is: are we going to reuse the network in the next time period as the initial message is propagating through the network? Or are we going to send a new message?
You're going to send a new message.
I
haven't defined messages. Remember? I have not defined messages. If I had defined messages in a traditional information theoretic point of view, I would have to have messages mapped onto code, which would give me a random process.
Sure. So maybe
Okay.
the next sample is random.
So what I have defined is I have defined a random process initially. Right? This is the random process. The random process is has an infinite number of samples in time. Okay? Does that answer your question? There's no messages.
Yes, although it seems like we're ignoring any interference between the next sample of the random process being sent through the network and the delayed previous sample of the random process going through the network.
Well, we can, okay. So I should have, other functions with memory are possible but not necessary. I wrote it there, but I didn't emphasize it. I could write something where I have a double summation, where I'm summing first over all the inputs, and then I could sum over past x's that have been received. Is that what you're asking? Okay, so I could have a system which has memory in the sense that a node puts an output, which is a linear function of its current inputs and all past received outputs. Let me write it right now.
It seems that on a slide you already showed us, we were looking at the determinant, which was a polynomial of the betas as well as the...
It's not really a polynomial of the betas and the d's. Okay, I mean, it looks that way, but I don't want you to think of it that way. It's a function of the d's. Okay, and the reason I don't want you to think of it as a polynomial of both, even though it is because I don't get to pick the d's. Right? The d is it's like a z transform. Okay, the z transform is a polynomial of the z's, but when I'm choosing the parameters that go into z transform, I'm choosing a function of z. Okay, so the d's don't get involved in making it come out to non-zero.
Suppose we satisfy that. We find some betas that give us non-zero.
Uh-huh.
It seems to me that that still doesn't guarantee that we can decode because there may be additional interference involved between the samples of X. But maybe I'm...
What do you mean by the interference on the samples of X?
I mean, we're looking at the transfer matrix for one input sample, or all the various X's at one time. How much they're delayed, that's what P gives us, right?
Right, and I could have memory. So I could hold, you could, but remember, it's not a channel with ISI, for instance, where I come and I give you the channel. I am picking the functions. right? So when you talk about interference, it means that somebody came and gave you a channel and they said, woe is me, I have ISI, so I'm going to have memory and have to work around it. Whereas what I'm saying here is not that. There is memory that comes from stepping through the network. And you can see how if you impose more memory, you can just step through more edges where one just feeds into the next one directly. Right? That makes sense, right? So if I have an edge with delay more than D, I can just make a series of edges, one which feeding into the other. But I don't have interference in the usual sense of having something which is interfering with itself, because if I want, I could put memory here. But it turns out it's not necessary. Okay, so we could put a memory here. I could put an extra sum here, which would take the x's in the past. Is everybody clear on this? Right? I'm not eliminating that possibility. If it makes, right? So that can hold. But it turns out that certainly for the multicast, you absolutely don't need it. Okay? And it's, yes, not necessary.
It's almost sort of an equivalent of the Shannon argument that if your channel doesn't have ISI, you don't really need to keep your past.
That's right. You don't need, exactly. You don't need to keep the past because you didn't impose having the past. Right. When we have cycles, it'll be different. Okay? No, there wasn't a question. There was a comment by Lalita saying that if you don't have memory in the system, there's no need to keep memory. Right. I mean, obviously you have to decode, you do, but not for the random process. Yes?
Will the same frame hold if the delays are not edge invariant?
If the delays are not what?
Edge invariant. Like the delays are assumed to be same for every edge.
Oh no, I just said it doesn't matter if you have delays which are different. Because, suppose that I have an edge with delay of 2. It's just like having 2 edges, each with delay of 1, one which only feeds into the next. Is everybody clear on that? So I didn't drop any generality by having a delay per edge of 1. Right? If I had a delay of 1,000 on an edge, it would just be 1,000 edges, one, in a daisy chain, one feeding into the next. Yeah? Any more questions? Yes, Paul.
Can I just, maybe this will clarify my question. Can I get you to draw a graph on the board that will describe my question?
Your question, well, I don't know. This graph does it.
Well, what if you have a graph where you split, you go from 1 node to 2?
Yeah.
And then the second goes across, yeah, okay, thank you.
Okay.
Maybe make sort of a triangle.
And wait. Before I make sort of a triangle, I sort of need chalk. Okay. All right. So I have is it a sort of or is it an actual triangle?
Make a triangle.
Make a triangle. Okay.
Okay, now put arrows on them so we get directions. Yeah, okay. Perfect.
Nodes?
And then, yes, and then from the place where the 2 arrows meet, draw a third thing out of whatever.
Okay.
Okay.
How's that different from this?
I see 2 paths with different delay, and I'm saying, what I just want.
These are not paths. These are incidences upon a node.
Yeah, my question isn't necessarily with this slide. I'm wondering, have we talked about like a capacity result? What would be the capacity of this network?
It would be the min cut. It would be the minimum of this and this.
What about the one, the single link over there?
Oh, there's one. Okay, and this.
So it would be 1.
In this case, the way you drew it, it would be 1. It's the minimum of the cuts, and these are the 3 cuts.
And that's where my question comes, because if you write out the matrix P, you get a D squared and a D, and it looks like. So
this is going to have D. This is going to have D. This is going to have D. That's okay.
Can I maybe make a comment?
Yeah.
You're going to have a decoder.
A decoder. That's yes.
And that will get rid of the interference inside the network.
Yeah, and we're going to go to that.
That makes it look like you'll get a capacity.
No. It's still the same. Look. Oh, I took it out. Look. I would.
0 is going to be a 1 coming in at time 10, depending on, or here 2 or something.
It's a convolutional code. Okay? Convolutional codes do this. Right? The output right now is a function of stuff that was put in the past. Right? And what do you do when you have a convolutional encoder? At the decoder, you're going to have to take a rational function in D's. Right? Strictly speaking, you would never end. but you know, of course we cut it. It's exactly that. It's a convolutional encoder. Does that make sense? So in a convolutional encoder, just because it was a function of something in the past, it doesn't change your capacity. So this is a convolutional encoder, and you would have a convolutional decoder, which means that this is, as Gerhard pointed out, you're going to have feedback in the D. Is everybody familiar with convolutional encoders and decoders? Do you know?
Yes.
Okay, so do you see why it is?
Yes, on a previous slide, I thought you had a result on how we would have a capacity, and it didn't seem to match up with how this went. But I mean, I'm okay to go on and figure it out later for myself.
So what is anybody else bothered by this? Yes. You're bothered. What bothers you? Okay. What bothers you?
Exactly the same question, because it looks like the two cuts are at different times.
No. The cut. No. The cut. Okay. Time. Forget about time. Okay. Who gives a hoot? This does not change your throughput. It's your actual throughput. Okay. Let me show you how you decode these puppies. Cheerleaders, I have 2 of them at home.
As an entropy, the overall entropy of the overall entropy of the output, you should be able to kind of see increase the entropy of the output.
You don't. Yeah. No. Let me show you.
But from statement 3 on that slide, it looked like it was
Okay, I don't know which slide.
Here, let me show you. It's the same slides, but let me show you the decoder, and this may make you happier. So I've taken stuff out of here. This is the more complete set. By the way, here is the okay. Here we go. I just didn't think this would be an issue, but it is. So that's good. Let me see. Can you let's see? Save. How does one do the Control L? Is it? Yeah. Okay. So the receiver terminal has to allow for rational functions. Okay. So, all right. Which means that the y, which is again, remember, an infinite sequence of y's with this d, right? The d is just there to show, the d is just a way to represent a long vector. Okay? So all I'm doing is, instead of representing this as an infinite vector, I'm representing it as a polynomial in d, just like a z transform does. Okay? So I don't want you to think of it as a polynomial in d. Okay? Forget d. D is just to say, this goes here, that goes there, but all I've done is I've just turned it into a vector. So now I have vectors going through my network, and at the receiver I have a vector. Okay. Now, strictly speaking, I would have to wait forever at the receiver vector to get back to the infinite vector of the beginning. Right? Because this goes into the memory, each element of this vector, where remember d is just the power of d is just indicating where in the vector I am. Right? I would never finish. I would never end. Every time I would say, okay, the symbol that I just got is a function of the following set of symbols, but by the way, those symbols are also going to affect me in the future. So I would always be running away from myself. That doesn't change the min cut. Time does not matter here with respect to the min cut, right? It's the entropy rate, as Gerhard pointed out. So what do I do at the receiver? Well, I have this vector of y's, right? And I'm trying to make a z vector, which is an infinite vector itself, out of those infinite y's. It never ends. It just runs away. It's a runaway system, if you will. But it's not a runaway system that we don't know how to use, right? We're used to using convolutional codes. Okay? So basically, what am I going to have to do at the receiver? I'm going to have to do two things. I'm going to have to, of course, look at all the input edges that I have, which is, right? And therefore, those input edges gives me the y's. And those y's are going to give me some processing, the xi, right? And then I also have to look at all the z's, at the whole past. So basically, in order to recover the z, I'm going to have a rational function in D, right? Which means that I can, basically what happens, I can make this as a shift register. I can implement this as a shift register. Okay, undergraduate, second year, third year, you get a function in D or in Z, and you make a shift register that implements it, linear. Except here it's going to have to be rational. Okay? This is just a convolutional decoder. Okay, so in practice it never ends, right? But that's never stopped us from making convolutional decoders, right? All right? Does that make sense? Does that remove your bother? Does that remove your bother? Yeah? Okay. All right, so obviously I should have left this one. But everybody happy with this? Okay. All right. So I have the exact, so basically it reduces to exactly the same problem I had before. Let me go now to the transfer matrix with delays and cycles, and obviously it sort of fell off because I had taken this slide off too. But now I can tell. It would not have been. So it's the same example as before, but I have a cycle going back. Okay? And what's going to happen here is, as somebody pointed out, this is no longer, even the F in this case is no longer upper triangular. Right? Not that the M ever was. Okay. But like I said, don't get hung up on upper triangular. But I need to have a delay there. Okay? So what happens here, I have 6 edges. Okay? I have here the incidence matrix. The D's, again, the D's are just there to count time, to know where in my infinite sequence I am. Right? Don't worry about them. I have a 6 by 6 matrix with rational coefficients. Okay? So now, the interest of having the D is that I can do this. I can have cycles. Well, I mean, it was nice to be able to have delays. Gerhardt.
Can I have self-loops?
You can have self-loops, but it won't get you anywhere. Does it
ever help?
Oh, that's a good question. Does it ever help to have self-loops? I can't even... I would have to think about it more, but I don't think it does because you can always have the function, the self-loop basically would allow you the current output to be a function of the past outputs, and because everything's linear, you're going to see that output in whatever shape you wanted it to be. Right. So, that contribution would not be able to show up in a better way. So I'd have to think about it more, but I don't think so. It's basically the same thing except in time. Okay? Okay? So there you go. Now you can have delays, you can have cycles, you don't need to be upper triangular. Right, you do need to do this, right? But I'm not going to reinvent the wheel. Right? It's a convolutional decoder of a linear system with delay. Right? Still time invariant. Right? So it's basically, again, what I'm trying to say is there's almost no coding here. This is all linear time invariant systems. This is almost just signal processing, just happens to be over a finite field. Okay? So don't be fooled. That's all it is. And this problem of recovering is exactly the same problem that you have if I have a feedback shift register. What do I do at the output to recover the input from a feedback shift register? I have to do this, right? Does that make sense? Okay. So let me now go back to my all right. Okay. So now the thing that we got this morning is basically I can take stuff, put it into a network. It's just a linear time invariant system with possible delay, and either I can make it invertible or I cannot. Right? Invertible may just sometimes be as easy as inverting a matrix. Sometimes I have to go through a function of D, but that's it. Now the question is, how do I find the xi's? Remember, let's go back to the question that we had at the very beginning here, which is, how do I find those xi's? How do we find a solution? Okay. I mean, basically at this point we have said either there exists a solution or there doesn't. If there does exist a solution, then as we bump up the field size, more and more solutions relatively to the size of the field I'm working in should pop up because the roots, which are the problems, don't go up. Okay? How can I make use of this to do something intelligent? How can I make use of this to do something intelligent? And this is it. Okay. So the effect of the network is that of a transfer matrix from sources to receivers. Delay or no delay, I don't care. To recover symbols at the receivers, we require sufficient degrees of freedom. That means I need to have an invertible matrix. Let's try now think without delay, okay, just to make our lives easier. So the realization of the determinant is going to be non-zero coefficients with high probability if the coefficients are chosen independently and randomly. Why? Remember, I have a certain number of roots, right? The probability that I hit those roots, if I choose them randomly from a finite field, is going to go down with the size of the field. So if I have a large field, the probability that I hit a root if I choose randomly out of the field is the number of roots over the size of the field. Well, let me go take that to the next step, and let me say, let me go to a large enough field, and let me choose the coefficients randomly. Every node is choosing its coefficients randomly. It doesn't depend on the data, it doesn't depend on the time, it doesn't depend on a darn thing. It just picks one. Yes, Alex?
So in one dimension, the number of roots is constant if the field is increasing?
That's true. So you have to change it a little bit. So I'll show you that in a little bit. So it's you're right. In multidimensional,
it scales, right?
It scales, but it doesn't scale as quickly as the right. So you're right. So there's a more or less equal. Okay. So one is scaling more slowly than the field size. Right. So the field size is scaling. The field size is scaling exponentially with the number of bits represented, whereas the roots are scaling much more slowly. Okay, so but this is just sort of the overview, and then I'll give you a little bit more detail. And with the delay also you have to be a little more careful. Okay, but basically, you're right that because it's a multinomial, not a polynomial, it would scale, right, but very slowly. So basically, I can use randomized network coding. Every node is going to choose the code randomly. Okay, and I'll show you some applications of that later today. But let's think about it. This is completely insane. Every node is randomly picking combinations of inputs and just spouting them off on its outputs, and that works. Right? I mean, it's so completely different from the way we've done networking. Right? So for all of you who come from information theory, like, oh, random's good. Yeah, random's good. It's bizarre, right? I mean, point-to-point random's good because basically, why is point-to-point random good? For this reason, right? Point-to-point random's good because, high probability is going to be invertible. But multi-point to multi-point random's good in the multicast, right? And this all comes from the algebra. How on earth would you prove it without having done all the algebraic stuff we've gone through today? Okay? So the randomized network coding can use any multicast graph which satisfies the min-cut max flow bound. And I'm not going to go into this. I had thought of actually doing, but you know, if people are really interested, I can do it because I do have a whole lecture on it. But again, as you saw, I had to take out a lot of stuff. For any number of sources, even when they're correlated. Okay? So you can basically consider, and we'll look at it a bit later today, you can basically do this even when the sources are correlated. Just like you would do Slepian-Wolf with correlated sources, you can do network coding with correlated sources. And you can do random coding. You have to be a little more careful. You have to do a binning argument, and you get the output if the entropy bounds work out. Okay, so we're not going to go into detail. Do you have a question?
Just a quick. So this is for the case where everybody wants all the information.
That's correct. Multicast. We'll go down to multicast later. Okay. This is for multicast. All right. So let me give you a bit of an idea of the proof. Okay. So you actually can get a slightly better bound. So for a feasible D-receiver multicast connection on a network with independent or linearly correlated sources, by the way. By the way, the linear also doesn't really matter, but it just makes it easier. A network code in which code coefficients for eta links are chosen independently uniformly over f sub q. The success probability from this random network coding is at least 1 minus d over q to the eta. Okay? Which basically means, since obviously d is not changing, as you bump up the field size, eta, the number of links, is not changing, right? As I make q larger, this is roughly going as, right? Okay? It's roughly go as 1 minus d eta over q. So as I bump up my field size, the probability of success is basically going to 1 as q becomes large. And of course, q is growing exponentially in the number of bits that I'm using to represent it. So my length of the code is giving me an exponentially better probability of the whole thing working out. Very information theoretic, very, very pleasing. Okay? And you can get error exponents in the case of correlated sources, and I'm not going to go at all into detail, but you can get error exponents. So how many people do, not everybody does error exponents. So this is not to, to shame yourself on it, it's for my own knowledge. How many people do error exponents when they do information theory? How many people did error exponents? Okay. So a minority of people did error exponents. Okay. How many people did error exponents for Slepian-Wolf? 1. Okay, all right. Well, okay. So you know error exponents for point-to-point channels. Okay, with random coding. So you can do error exponents for Slepian-Wolf. Everybody knows Slepian-Wolf? Yeah. Okay. So you can do error exponents for Slepian-Wolf. Those are the Chizar error exponents. Basically, you take a random code and you can find an error exponent, which has terms which depend on the Kubo-Lieber distance between a variety. Anyway, if you have there are error exponents. Basically, if you use random network coding, you find error exponents with correlated sources. You find error exponents on the entire thing, which in the special case where your network has a depth of 1, in the special case, so Slepian-Wolf is a special case with a depth 1 network, right? Yeah? You have 2 sources, 1 receiver. So in the special case where you have 2 sources, 1 receiver, or multiple sources, 1 receiver, which is Slepian-Wolf and depth 1, those error exponents are exactly the Chizar exponents. Okay? So you can have error exponents with correlated sources, which will have a dependence actually on the depth of the network, the maximum path length. All right? So obviously it's way too advanced for sort of a more introductory class like this, but I want you to keep that in mind. We'll show a little bit of that when we look at optimization. All right? This distributed random coding, which I'm sort of just saying, ta-da, out it comes out of the algebra, actually gives you some very powerful, very, very powerful results. Okay? Which means that as long as the entropy cuts from the sources to every receiver are not violated, then we can reconstruct at the receiver. Okay? Okay, all right. Okay, so this is, and let me just give you an outline of the proof because it's a little cute and it gets a bit into this question of that Alex asked about the growth of the. So basically, recall that the transfer matrix for each receiver has to be non-singular, and basically, you can bring back the problem of finding a non-singular transfer matrix with the pre-processing, the stuff in the middle, and the post-processing. You can turn it into an Edmonds matrix. Now, what do we see Edmonds matrices? Bipartite matching, for instance, right? Just to give you an idea, how many people have done Edmonds matrices and bipartite matching? How many people have taken sort of algorithms course? Oh, 2. Okay, so all right. No, 3. Oh, no. I didn't know. I mean, I'm trying to gauge. Okay, so does everybody know what a bipartite match is? Yeah, I see a lot. Okay, so there's specific ways of dealing with bipartite matches, and one of the ways that, and you know, if you take a course, for instance, in randomized algorithms, one of the prime examples of how well randomized algorithms work is actually using Edmonds matrices for bipartite matches. Okay, and choosing the coefficients randomly. So basically, you can bring it back to an Edmonds matrix with possibly a delay. Okay, and this would look very much like, again, something that you would see in a randomized algorithms class, right? This would look like what we developed here because we need a D, right? Normally in bipartite matching, there's no D, okay? And what am I going to do? Well, I'm going to choose exactly what we do in randomized algorithms, which are, I'm going to use a Schwartz-Zippel theorem. The Schwartz-Zippel theorem is basically the theorem that says have a non-zero polynomial, pick the coefficients randomly out of a large enough field, highly likely that it's going to work out. Okay? But this takes care of the point that Alex was making, that there's a subtlety there with the growth. Okay? So basically what you want is the product of these receivers determinant polynomials to be non-zero. And what you do is you have to set up an induction on each xi. Okay? But each xi, of course, has an exponent of most d. Okay? And that's how you get this. So the particular form of determinant polynomials gives rise to a tighter bound than Schwartz-Zippel for general polynomials with the same total degree. So it's a little better than, so what I'm saying is, to get this versus just getting eta d over q is actually requires an inductive proof. But in the end, as q gets large, it gives you the same thing. All right? So either, so I want you to, so one or two things. Either you have never seen a randomized algorithm and it doesn't matter, this is the thing that matters, or you're a randomized algorithm jock, in which case, the endorphins should be flowing at this point. All right? Either way, there should be endorphins going. Okay? But you see what I'm saying, right? The main thing is you choose these coefficients randomly, and you can deal with this d, it doesn't matter. The big D, the delay. All right? Are there any questions at this point? So everybody's happy with randomization? Yeah? Good. All right. Okay. Now at this point, you should start to think about things. Somebody had asked me earlier this morning about, well, what about packets? How am I going to do this in packets, right? And actually, let me go all the way back to. So remember, at this point, everything was synchronized. Life was good, right? This is. Let me go back all the way here. Once I've mixed this data, what happens if I lose this guy? I mean, before, when I wasn't mixing data, if I lost one guy, well, at least I had B1 or B2. Right? It was something. Now I get B1 plus B2. If everything was properly uniformized by doing the right sort of source coding, actually B1 plus B2 should have 0 mutual information with respect to B1, 0 mutual information with respect to B2, original one-time pad. We might look at that later today if we have time for security, okay? I mean, it has some mutual information with B1 and B2 jointly, but it's 0 with respect to B1, you know. Well, now what did you do, okay? So now, is it going to be the case that I lose one packet in my system, which of course is in you know, most modern networks happens all the time, and I end up, you know, completely screwed up because I've made it, you know, I've sort of made this exquisite algebraic construction. Okay, it's not exquisite because it's random, but still, you know, this algebraic construction. Now I miss one packet, and now what do I do? Okay. So at this point, you know, something should be telling you that, you know, this model almost is starting to look too good to be true, right? Every node just randomly mixes and off it goes. Okay. Well, on the other hand, if I miss one packet, it's because I didn't get enough degrees of, then I can't invert because I didn't get enough degrees of freedom. I only got one equation, I needed 2. Well, as long as I get another equation down the road, I'll be okay, right? So I don't need stress, right? I can't get 2 packets from getting 1 packet, fair enough. 1 coded packet. I can't get 2 uncoded packets out of 1 coded packet, but okay, let me just wait for another coded packet to show up, and when it shows up, I'll do it. Okay? And that's exactly what we're going to do, and the random coding is going to help us in this. Okay. So let's look at erasure reliability. So when you have erasures, well, you know, you have congestion, you know, packets get lost in buffers, outage due to fading, change in topology. I mean, there are all kinds of sad stories as to, you know, why packets meet their demise inside of network. And the prevailing approach for reliability inside networks tends to be request for retransmission. Right? Not entirely, but that's basically, for instance, something like TCP is end-to-end request for retransmission. But we'll see later, of course, you don't have to do it just that way, right? You could do it inside the network and so on and so forth. Okay? Now, the problem is, if I have a very high loss environment, I would be sending quite a few retransmission requests. For multicast, you have a problem where you have you know, particularly if you're doing end-to-end, I may be sending a lot of retransmissions because only one node didn't get it. Right? And you have all these typical problems that people deal with in networking with multicast when you just have this proliferation of acknowledgments, or else you have way too many retransmissions because of just one bad link for one receiver. Okay? And of course, there are issues for real-time applications. So by the way, this is the second part where I said I would, you know, was going to start leaving behind a little bit the algebra and get a little bit more into networking. Okay? But we'll revisit the algebra later after you've been refreshed by lunch. Okay? So what do people do? Well, you can do forward error correction, a variety of things you can do. You can do multiple description codes. You could do multiple resolution. You can do end-to-end erasure correction. And of course, you could use something, you know, classical like Reed-Solomon. Or you can do codes that are more designed for networks with erasures, you know, with fast decoding, tornado, Ruby transform, whatever you want. Basically, the end-to-end argument is that the connection as a whole is viewed as a single channel. So, you know, I'm connecting to the back of the room, maybe through all these people in between, but, you know, the whole network was just a channel between me and my receiver or receivers. That's the basic view. Okay? So I'm doing things at the beginning, at the ingress of the network does things to me, and the receiver tries to reconstruct what was sent, you know, taking a fatalistic view of what happened over the network. All right. So let's look at something very simple. Okay, so this is like classic example straight out of Blayhood's book on information theory. All right, 3 nodes, 2 links. Okay, and I have an erasure probability epsilon AB on the first one, epsilon BC on the second one. So what happens if I do end-to-end erasure coding? My throughput, my capacity is this. 1 minus epsilon AB times 1 minus epsilon BC. So probably the packet gets through. Right? And I have to code in order to make it a capacity. But I basically have an end-to-end erasure channel with the following capacity. Right? Erasure is simple because the capacity is 1 minus probability variation. If instead I did it as 2 separate channels, so I encode at A, say block encode at A, block decode at B, block encode at B, block decode at C, then I'm going to get the min cut, which is the minimum of the 1 minus epsilons. Okay? So that's actually the capacity of that network. So network coding, the minimum cut is, of course, the capacity. What happens? Well, for erasures, correlated or not, in the multicast case, I can deal with the average flows uniquely. Okay? Now, you would think at first that I have to keep track, and this is what this work does, have to keep track of what happened at each point in the network. Right? So say, you know, packet 5 that was coded with packet 7 got lost on edge EIJ. You know, sort of the sad story of everything that happened. But do I really need to do that? What does the receiver care about? Does he care about how deep the network was? The sad story of what edge did what to what packet? Or does it just accumulate degrees of freedom until it can invert? Wait.
The second one.
The second, yes, thank you. Of course it's the second one, right? It doesn't care. All it cares is, it's not that, so now we have something which is stochastic. But again, all I care about is the end at the receiver. What I, as a receiver, what I really care about is what the impulse response was. And sometimes I'll have an impulse response where certain coefficients got set to 0. Okay, you know, I'm the receiver. What can I do? It just keeps sitting there until I get enough to invert my matrix. All right? So the nodes store receive packets in memory. Random linear combinations of memory contents are sent out. Now, why is it important here? Remember that when I did delay before, I said for multicast, I did not need to keep track of what had happened before. Right? And you had a question about that, about, you know, was I losing something? And I think this is getting to that. Why do I need to keep track of it now? Of what happened in the past? Why should my nodes combine not only what they just saw, but things that they saw in the past? Pardon? It's actually not the time variance. That's a good guess. Why do I need to keep track of what happened in the past? Because of the erasures. That's right. Because of the erasures, I might have gotten lost. Right. So I need to keep track of everything that I saw in the past, and a node at the input is going to send me something which is encoded, you know, random linear coding of what it has. Every node in the intermediate steps is going to take random linear coding of everything it has and to send that out. Okay? So there are delay expressions. I'll talk a little bit more. I'll talk a bit about the Jackson networks, and it can be used, of course, in a rateless fashion. Why is it rateless? It is rateless, right? I have a file, for instance, I'm just sending random linear combinations until everybody gets it. Until everybody says, I've got enough degrees of freedom to invert my matrix, thank you very much. Okay? So let me actually, I'm not going to do this because I have spent too much time on other stuff, but I can come back to it if you want. So for erasures, correlated or not, like I said, I can, in the multicast case, deal with just average flows. Okay, so the node store receiver packs in memory, send out these mixtures. And one thing that's very important is I'm not waiting for the full block as an intermediate node. As an intermediate node, I'm not doing a block coding where I'm waiting for an entire block and able to, you know, decode it or do whatever. I'm just sending whatever I got whenever I got it. In general, actually, I might not even be able to decode it. I may not even get to see enough degrees of freedom to decode it because many nodes may be contributing. Okay? So the scheme gets to capacity on the arbitrary coding at every node for unicast and multicast connections, and actually point-to-point and broadcast links. So let me just give you a brief idea of how you do this. So basically, I'm going to have k message packets, and now I do have messages. Going back to Paul's question before, fixed length vectors at the source. And I'm going to do uniformly random linear combinations of these messages, which are injected into the source. Okay? Every node takes the received packet stored in memory and is going to, in every packet, put a header, which is a length k vector over fq representing the transformation of the original messages. Think that these are original packets. I want to send k packets. So a packet itself has a header which says, I am a packet, who is composed of alpha times packet 1, beta times packet 2, gamma times packet 3. This is my description as a coded packet. This is the code which I carry with me. So an initial